Hi everybody, welcome back. And let me try to remind you what we did last time. And last time we were studying the permutohedron, right, and the basis of the permutohedron. So we showed that the faces, the k-dimensional faces of the permutohedron are in bijection with partitions, ordered set partitions. Of bracket n into k disjoint part, non-empty parts. In particular, there's n factorial vertices and 2 to the n minus 2 facets. And in general, the number of for arbitrary k, what you get is k factorial times s of n comma k, where s of n comma k is the Stirling number of the second kind. So in other words, these count unordered set partitions of bracket n into k parts. So, and then you multiply by k factorial, and so you get ordered set partitions. And this is all very nice. And today I'd like to sort of continue to study the properties of permutohedra. And in particular, in the last lecture, a few people mentioned the Bruhat order. So, and probably many of you haven't heard of it. So let me try to start by explaining what does it have to do with the Bruhat order. So, and okay, so Bruhat order. First of all, order. Order means it's a poset. Let me, just in case, let me define posets, which are, so a poset is also known as a partially ordered set, is usually written as a set with a binary relation, has to satisfy the axioms, some very natural axioms like transitivity. If you have x, which is less than y, less than z, then x is less than or equal to z. And the other one has to be reflexive for all x in P, and it also has to be antisymmetric. Right? So this is a partially ordered set, and and in particular, we're going to be interested in how you can actually very compactly describe the poset. You can only remember sort of the smallest non-trivial relations, and these are called hovering relations. By definition, you write x less dot than z if there does not exist a y in P such that x is less than y less than z. If you can't put any element strictly between these two, then you say that z covers x. And in particular, if you know all of these covering relations, then using transitivity, you can recover the whole poset. So we like to draw posets using these covering relations, and that's called the Hasse diagram. P is just a graph. It's a graph where vertices, the vertex set is P, and edges are the covering relations. For example, I can draw you a Hasse diagram. Here's a Hasse diagram. Usually it's drawn from kind of the smallest elements are at the bottom, and it's all directed upwards. So this Hasse diagram here, encodes a poset which is given by A less than B, A less than C, and B less than D, C less than D. Right? But B and C are incomparable. And you can also, well, we also have A less than D by transitivity. And these are A less than B, A less than C, B less than D, C less than D. These are all covering relations. But this guy is not a covering relation. Right, so I should define less, by definition, x less than y if x less than or equal to y, but x not equal to. Thanks. All right, so you have these natural partially ordered sets, and then I would like to study the Bruhat order on the symmetric group. So my set and that is going to be called the weak Bruhat order. Sn less than or equal is, well, it has covering relations as cover relations given as follows. So you write V is covered by W for two permutations V and W if and only if and only if W equals to, if I have to choose one of the two sides, V times Si for some I in bracket n minus 1, and the length of W is the length of V plus 1. So what do I mean by the length here? The length is, by definition, where the length of a permutation is just the number of inversions. Yeah. Yeah, it's considered directed upwards always in all of my pictures. But yeah, usually I just drop the arrows. Okay, so what are we doing here? We are taking one permutation is bigger than the other if it's obtained by, so here Si is a, what is called a simple transposition. Right? You swap positions I and I plus 1, and the length has to go up. It either goes down by 1 or up by 1. And W is bigger if it goes up, otherwise it's. So, example. What happens for n equals to 3? What picture? We have identity at the bottom. 3 to 1 at the top. Nice. Two, 1, 3, and 1, 3, 2. I'm trying to apply simple transpositions in all possible ways. And then what do I do next? Okay, So I get a picture which looks like a hexagon. All right, very nice. And of course, by what we showed here when two vertices form an edge. When the two vertices of the permutohedron form an edge, well, precisely when they differ by, the two permutations differ by a simple transposition. So in particular, you can write that in the following way. You can say that corollary is that the permutohedron is, okay, let me do it this way. The one skeleton of the permutohedron is the Hasse diagram. It's equal to the Hasse diagram of the weak Bruhat order on a SAM. Okay, so you're saying I have to relabel permutations by their inverses in order for this to make sense. Okay, yeah, I should swap these two. One or the other is going to work. And these two definitions of the Bruhat order differ by replacing each permutation by its inverse. Oh, wait, seriously? No, I think this should be right. Okay, so let me, if I multiply by psi on the left, means I'm swapping positions, adjacent positions. And in this picture, I'm always swapping adjacent positions. So this works. All right. So, and this, why should this be surprising? Of course, it's not surprising to you because we already proved kind of the same interpretation of the edges in the previous lecture. But if I just erase your memory and start talking about the symmetric group and inversions and the Bruhat order, there's no a priori reason it should come from some polytope. It's for higher n is going to be a gigantic combinatorial picture. You try to draw it in the plane, it's going to be complete mess, but somehow it comes from a polytope. That's pretty nice. So, and that's sort of what happens in general. Nice combinatorial objects like to be derived by polytopes. And while I'm here, let me justify the weak. Why is it called the weak Bruhat order? Because if you go and read some papers, you're going to discover that there is something called the strong Bruhat order, which, or even if people say just the Bruhat order, they mean some different. Definition, strong Bruhat order, or sometimes just the Bruhat order means strong Bruhat order. Is, well, it has S-cover relations. V is covered by W if and only if W is equal to the left an arbitrary transposition of I and J times V, and the length of W should again differ by 1 from the length of V. So here you're allowed to swap any two, not necessarily adjacent entries, but you have to make sure that the number of inversions increases by exactly 1. Then they form a covering relation. So what's the picture here? I still have all the, well, I have to check that they are covering relations still, but definitely these are the all still relations, because I can take my transposition to be adjacent. Do I get anything else, or is it just a vertical line? Okay, I get a vertical line like this. But notice that this is not a covering relation, because I already know that 1 to 3 is less than 3 to 1, because there is a chain of inequalities. So this actually, I mean, I can draw it, but it's to get diagonal ones. 2, 1, 3 should be less than 3, 1, 2, because I can swap 2 and 3, and I'm going to add exactly one inversion. And I'll probably also get the other one, right? So that's the picture of the strong Bruhat order. And you should all memorize the weak Bruhat order looks like that, and the strong Bruhat order looks like this. And so here's the question. Is this picture the one skeleton of some polytope? Okay, so you're saying that this triangle here belongs to this quadrilateral face and also to that quadrilateral face. So all of these 5 points should be in the same plane, and that's bad. Well, I mean, you still have to prove it that if you have like a square in your graph that doesn't have to come from some face. Maybe it goes around the polytope. So it's, yeah, but it's still kind of an argument like that should prove that this cannot come from any polytope. And that illustrates my previous point that if you start with some arbitrary thing, then it doesn't have to come from a polytope. But still, so I'm not going to actually discuss this too much, but let me just mention, because I think it's pretty cool. So still, it is the one skeleton of some other object which looks like which is not a polytope but looks like one, of something that's called the totally non-negative flag variety. And this works for arbitrary n. It's denoted FL n greater or equal to 0. And so again, I'm not gonna, this whole stuff comes from the theory of total positivity, but let me just draw a picture. So the picture looks like this. You should imagine a three-dimensional ball, which is bounded by a two-dimensional sphere with 6 points here on the boundary. And then you have these edges which kind of go like this. 1, 2, 3, 2, 1, 3, 2, 3, 1, 3, 1, 1, 3, 2. So, and then you should kind of, there is a quadrilateral face which is glued onto the sphere here, and there is a quadrilateral face here, and there's one over there, and there's one down below, and there is a three-dimensional thing inside. So this has faces, but it's kind of like a curvy polytope. It's one skeleton. One skeleton is, by definition, it's a graph where the vertices are zero-dimensional faces and edges are one-dimensional faces. So if you have a polytope or some other complex which has faces of different dimensions, then you just take the 0 and 1-dimensional guys and you get a graph. So in particular, there is a way to think of this geometrically, and I can explain the flag variety. It's easy. The flag variety FL sub n is, by definition, you take this set of all flags. flag is a sequence of linear subspaces. Go all the way up to Vn is equal to R to the n. So you get these 0-dimensional, 1-dimensional, 2-dimensional linear subspaces. So dimension of Vi is equal to I. Yeah. So, and then there's some, the picture you should imagine is that there's the origin, and then there is a 1-dimensional subspace, which is V1. And then there is a 2-dimensional subspace, which is 2. So each such sequence represents one point in the flag variety. And some of these points are totally non-negative, and some are not. And those that are totally non-negative form a geometric object, which looks like this. So it's actually, yeah, anyways, there's a whole branch of research which comes out of you have a natural combinatorial object, and you find a nice geometric interpretation. And this actually, it's a very recent result that this thing is like homeomorphic to a ball, and all these cells are also balls. So yeah, that's a quick detour on the strong Bruhat order. Any questions on this? No questions? So let me now mention, because we're going to study some generalizations of permutohedra, so let me discuss a few other properties of permutohedra. So I think these are pretty mind-blowing if you've never seen these before. So there's going to be 3 properties, and I'm going to prove only 2 of them. So the first one is that, well, remember what's the dimension of this guy? N minus 1. Okay, that's true. Dimension is n minus 1. So the claim is that the n minus 1 dimensional space can be tiled by permutohedra by shifts of copies of it. For example, for n equals to 3, the permutohedron is what? A hexagon. Can you tile the plane by hexagons? Very nice. Okay, I'm going to draw this hexagon. Etc. And we have these coordinates: 1, 2, 3, 2, 1, 3, 1, 3, 2, and then I actually should label them by inverses. Sorry, I want to label them by actual coordinates. 3, 1, 2, 3, 2, 1. Okay, so of course this is what happens in 2 dimensions. How do I write down I have to shift each copy of the permutohedron by some vector. How do I write down the coordinates of these vectors? And that's actually pretty non-trivial to figure out in n dimensions. So let me just tell you the answer. Shift a copy of the permutohedron by all vectors of the form. So we have vectors x1, x2, all the way up to xn inside z to the n, such that they sum up to 0 because you want to stay inside this n-1 dimensional space. And also, all these coordinates have to be equal to each other modulo n. So the claim is that if you take, it's a certain lattice inside the n-1 dimensional space, and if you take all those points and you shift your permutohedron by all these points, you're going to tile the whole space. So for example, let's say this point here has coordinates 0, 0, 0. What are these neighboring points? What is this one, let's say? 1, -2, 1. Okay, so take this vector from here to here, and you add it from here to here, right? That's the... okay. What about all the other ones? Here? 2, -1, -1. Oh, I can actually write down their negatives as well. -2, 1, 1. And what's the other one? 1, 1, 1. So 1, 1, 1 does not sum up to 0. 0, -3, 3 is, well, that's actually interesting. Where is 0, -3, 3? Do you think it's over here? Far away. Okay, what's this one then? -1, -1, 2. Okay. But, sure? Oh, okay. Okay, 1, 1, -2, -1, -1, 2. All right. And I guess if you sum up, wait, what do you have to? No, that's tricky. Oh, okay, if you take the sum of these two vectors, then you get together, you get 3, 0, -3. Yeah, so you get all of such vectors from, and this works in any dimension. So, and for some reason which you're gonna see later, I'm not actually gonna give you the proof. So the proof is an exercise, which you can actually do. I think you can, because you know the description of all these faces of the permutohedron. Yeah. So you can, I guess the official definition of a tiling is that, yeah, the interiors have to be disjoint, the closures have to cover the whole space, and the intersection of any two has to be their common face. And we're going to study subdivision, because we're going to study triangulations and cyclotopal tilings later, so we're going to look carefully into what can go bad with subdivisions, but here this is very nice. And you can go on Wikipedia and look at the three-dimensional picture of actually, so I gave you all these pictures last time. Yeah, you can tile. It's kind of weird that you can tile the whole three-dimensional space by these pictures, but you can't. And Wikipedia tells you how. I mean, I already told you how. So anyways, that's the first fact. And it's nice, but let me tell you some other fact that's also nice. Fact number 2 is that, well, I have to remind you about the Minkowski sum. Remember, if you have two subsets of R to the n, P and Q, then their sum is just the set of all pairwise sums. So, all right, so the claim is that the permutohedron is the Minkowski sum of a bunch of smaller polytopes. Okay, let me write it down this way. I'm going to write it down in a slightly complicated way. So first is I just take the constant shift all coordinates by n plus 1 over 2. That really doesn't matter from the point of view of considering after translation. What matters is the rest. And the rest is 1/2 times the sum over alpha inside phi plus of negative alpha on the line segment from negative alpha to alpha. Which, okay, so what is, I mean, I have to explain what is this phi plus. So phi plus, where plus is by definition the collection of all vectors of the form Ej minus Ei, where I and j are, I is less than j, and they're between 1 and n. So I'm taking all pairs I less than j, and then I'm taking Ej minus Ei, and then I take it. So basically, each of these line segments is, you have the origin, you have Ei minus Ej, you have Ej minus Ei, and then you take that line segment, and you take the Minkowski sum of all of these. And by the way, this is called, phi plus is called the set of, because we're going to discuss this later, so be prepared. This is the set of positive roots. I'm going to define this later, of the root system of type A n minus 1. So for now, you don't have to pay attention to this, but it's what it's called. It's called the set of positive roots of A n minus 1. So how do I draw a picture? What happens, let's say, for my hexagon is it's gonna be a sum of some number of line segments. How many line segments am I going to get? I have the hexagon. By n should be equal to, according to that statement, it's equal to the sum of some number of line segments. How many do I get? 3 choose 2. So that's three line segments. Okay, and I can actually draw the root system for phi plus is, so we have E1 minus E2, E1 minus E3, and E2, I guess is the other way around. E2 minus E1, E3 minus E2, and E3 minus E1. And they all belong to the same plane where the sum of coordinates is 0. So I can draw them in the plane. And they look like this. There's a 60-degree angle, E1 minus E2 minus E1, E3 minus E2, and then E3 minus E1 is the sum of these two. So if I take the sum of the corresponding line segments, I guess I should draw my picture. This hexagon is equal to the sum of this line segment plus this line segment plus this. It's a sum of 3 line segments which form 60-degree angles with each other. And indeed, we can take the Minkowski sum. So they all have equal length. So if let's say I take the Minkowski sum of these two, what do I get? I can't hear you. Yeah, just take the first two and take the Minkowski sum. So what shape am I going to get? Parallelogram, okay. And then I add another one, so I can kind of add it to all of these points. we get is a hexagon. So I imagine that the origin is here, even though it's not, and then I'm just drawing it from all points direction. Okay, it works. And similarly, this shape is going to be the sum of how many line segments? 6. Okay, yeah, and you can actually, if you look very closely, I don't know how many has to have the picture, probably not many. I can distribute these as well. Yeah, but the edges of this polytope actually split into 6 families of parallel line segments, of mutually parallel lines. So if you just distribute this, there's probably not enough, but yeah, anyways, that's the second fact. And before I prove it, let me mention the third one. Because the third one is even better. I think it's even better than the first two. The third fact is that the permutohedron can be actually written as a Minkowski sum of a different collection of polytopes, which are not line segments and which are things that we already saw before. Permutohedron is the Minkowski sum of hypersimplices. Delta 1n plus delta 2 comma n, etc. plus delta n minus 1 comma n. And that looks kind of confusing because these are like octahedra or whatever. But let's actually see what happens for n equals to 3. So for n equals to 3, my hexagon should be equal to the sum of what polytopes? So first of all, how many polytopes am I going to get? 2. Okay, delta 1 comma 3 plus delta 2 comma 3. And how do these look like? I'm sure it's right triangle because, okay, so the picture is each hypersimplex, as you remember, is a section of a cube. So this is delta 1, 3, and this is delta 2, comma 3. And they lie in different planes even. But they're not right triangle, they are equilateral triangles. If you project, then you get right triangles. But if you just take on the nose these deltas as they are defined, they are actually equilateral triangles. This is equal, and one is upside down from the other. So what happens if I take the Minkowski sum of these two? Do I get a hexagon or? What do you think? Yes. All right, so let's say I choose the origin somewhere in this triangle, and then I take the first triangle, and then I draw all copies of the second triangle from all points. Something like picture like hexagon. And in particular, this picture, this permutohedron here is the sum of which polytopes? Oh, okay, that's true, right? So the the three-dimensional permutohedron is you take the tetrahedron plus the octahedron and they have to be positioned in the right way for the sum to work, but in this sum they are already positioned in the precisely correct way, plus the upside down tetrahedron. And this is already a pretty hard exercise for your 3D imagination. Yeah? Yeah, this is an exact equality. And that also, yeah, both of these are exact and not just up to scaling or shift on the nose. And I'm going to try to prove this. How do I prove these statements? Any ideas? Yeah? Oh, showing that this right-hand side is contained inside here is pretty easy. How do you show that? You just look at the which coordinates? Sums of the coordinates. Okay, so you're saying that each, here the sum of coordinates is equal to 1, here it's equal to 2, here it's equal to n minus 1, and here it's equal to n plus 1 choose 2. I mean, you show that they lie in the same, the right and the left-hand side lie in the same n minus 1 dimensional hyperplane. But oh, so you want to act by Sn and figure out the vertices. Oh, you're saying it's, oh, I should start with 0. Okay, maybe. All right, maybe they should be. Wait, is that? Okay. Yeah, all right. Yeah, let's call it delta. No, let me actually. And what? Oh, but I think it should be okay. 1 1. Okay. 1 1. Okay. Thanks. All right. So yeah, and if you want to compare these two, you can say that these both are symmetric. So we can somehow compare their sets of vertices, and we only have to look at one vertex. But then, what is even, like, if I have a Minkowski sum, what's the set of vertices of such a Minkowski sum? Okay, so if I pick a vertex from each one, is it always going to be, let's say, if I okay, so you're saying each vertex of this sum is of the form vertex of this guy plus some vertex of this guy. Okay, that is true. And maybe this way you can show that the vertices of the permutohedron are, well, I mean, you may get too many vertices, right? You can, somehow you have to know exactly which sums of vertices are give you vertices and which sums don't give you vertices. Otherwise, you get a large set here and a small set here, and then you have to, like, this set is inside this set, but then how do you go the other way around? So yeah, let me actually state a lemma. I'd like, because it's going to be very useful. There is a criterion for how to describe faces of Minkowski sum in terms of the faces of the summands. So remember that if you have a vector h in R to the d, then the corresponding face of your polytope consists of all points which maximize the dot product. So a very useful lemma is that f sub h of p plus q is equal to what? Can somebody guess? The sum of vertices. But let's say it's not even vertex, can be arbitrary face. The sum of, okay, so you want to choose the corresponding, okay, it's the sum of the corresponding faces h of p plus f sub h q. Very nice, yeah. So you get this very simple relationship. To describe faces of the Minkowski sum, you get to choose, well, you have to choose all possible these h vectors, but then you're done, because if you know, for each of these, if you know the maximizing phase, then you know the total phase as just, so each phase of this Minkowski sum is itself going to be a Minkowski sum, a bunch of phases. Yeah. So, for example, I should show you an example. Maybe I take this example here. So let's say I choose a phase of my permutohedron. Maybe this phase, f sub h of pi n. Then I should choose h to look up. Then what are going to be the phases of these line segments corresponding to h? Plus what? 2 top points. And indeed, so you get this line segment by taking this one and shifting it by these 2 points. Okay, so it actually works. Yeah, and proof is pretty straightforward. You just use this definition to kind of maximize the product. Easy. And, well, exercise. But, and I guess now, I guess I should just continue. I have 1 more minute left. Yeah, anyways, using this lemma, it's very easy to prove both of these facts just directly. And I'm going to do this next time. So thanks a lot, and I'll see you all on Wednesday.